In this video, we'll walk through the mechanism for the reactions of aldehydes and ketones with primary amines. So this mechanism has two parts. We have the addition of an amine and then the elimination of water. So we'll start with the addition of amine. We'll start with cyclohexanone. You could follow the same mechanism with different aldehydes or ketones. But here we'll start with this ketone, and then we will add methylamine. So the R group in the primary amine is the methyl group. Now, nitrogens, when they are neutral, have a lone pair of electrons, and nitrogens are not very electronegative. They are electronegative, but not to the same degree as oxygen. I'm looking over here because my periodic table's over there. Not to the same degree as oxygen or halogens or some other atoms on our periodic table. So although it has non-bonding electrons and it's not very electronegative, so it will react as a nucleophile. So with a nucleophile present, the nitrogen will create a bond to our carbonyl carbon. The electrons will be owned by oxygen then. So an amine is a strong enough nucleophile to add to that carbonyl carbon. Now I mentioned in the previous video that we do this reaction in a buffer solution, typically, with a pH of 5. In a buffer solution, we have acid with a buffer pH of 5. We have acid and conjugate base present. With a lower pH, our acid is a little bit stronger than the base. After the mechanism, we'll discuss why a pH of 5 is used. But when we have a buffered solution or solution with an acid or a base, just like we did for the acetal and the ketal reactions, where we had neutral solvent and protonated solvent present, well, we'll say that we have some acid, HB, and some base, just neutral B, available in solution. We'll use them as needed. We actually don't need them in this very next step, but we will when we do the loss of water. So we'll say we have HB plus some acid and then B with electrons as the base. And I'll be explicit here, the B does not represent boron. I just chose a B for base. You could make that an A for acid if that is less confusing. Okay, so we've added the nucleophile, the amine, to the carbonyl carbon. The carbonyl oxygen now has a negative charge. Our nitrogen is still bonded to 2 hydrogens and the CH3 group. So nitrogen has 4 bonds here. It's got a positive charge. Now in this molecule, we have an oxygen with a negative charge that would be neutralized with a proton. We have nitrogen with a positive charge that would be neutralized if it gave away a proton. The oxygen and the nitrogen that can give away a proton are close to each other. They're already near each other in this molecule. And so we can do an intramolecular proton transfer reaction where the oxygen takes a hydrogen from the nitrogen. And that neutralizes all of the charges that we need to neutralize. So we have an alcohol, and now we have a secondary amine. And we'll call this our addition compound. So that's our first step, addition of amine. We've created that addition compound. And then the second part is elimination of water. So we have our addition compound. We have both an OH group and our now secondary amine. And we're going to eliminate water to create that final product. The final product is that imine. We have a double bond between the carbonyl carbon and the nitrogen. And so we can create that double bond by the loss of water. Now with the buffer solution, we have both acid and base present. So I will write that generic acid molecule Hb+. The oxygen will take a proton from the acid that's present, and then our B+ will just become a B. With this protonation step, we now have a substituent H2O, which we know is a good leaving group. So this is where that water byproduct is generated. So here's our good leaving group, which will leave. And instead of opening the shell of that carbon, the nitrogen, which is a good nucleophile, a good base, good atom to share electrons, will create a double bond to the carbon, and then the carbon to oxygen bond breaks and water leaves. So now our molecule of interest, we have a carbon to nitrogen double bond. The nitrogen is bonded still to a CH3 and another hydrogen. But now this nitrogen has 4 bonds, so it has a positive charge. We've lost H2O. And so now the base in our buffer solution will remove that hydrogen, give electrons. I'll use my pink arrows. The base will remove the hydrogen and give the electrons in the bond to nitrogen, so we get our final imine product. And again, we can encourage the reaction to proceed in the forward direction by removing water, so taking water out of the reaction flask, and also adding heat to increase the reaction. So back to this buffer. Why do we use a pH of 5 buffer? Well, we need the solution to be acidic enough to protonate our oxygen. So that occurs here. But it cannot be so acidic that it's protonating the carbonyl oxygen, or really what we're worried about is that amine molecule. So the amine that we're starting with, if that were protonated, it wouldn't act as a nucleophile. So let's write this down here. Buffer solution with pH of 5 is acidic enough to allow for protonation of this OH. But is not so acidic that the amine is protonated. If this occurred, the amine would lose its nucleophilicity. So if our amine gets protonated, in this case we used methylamine. So if methylamine is protonated, that nitrogen gains a proton, then it has 4 bonds, a +1 charge. The nitrogen no longer has electrons that it can donate to create a bond to the carbonyl carbon. The amine is a stronger base, so that nucleophile is a stronger base than the carbonyl oxygen. So if we're at a pH where the nucleophile is not going to get protonated, the nitrogen's not going to get protonated, then the ketone oxygen certainly wouldn't get protonated either. Now in the previous video, I showed an example, I'll scroll up here, where the buffer solution was specifically with acetic acid. Well, acetic acid has a pKa of, I believe, 4.8. So we're right at near the pH of 5. So acetic acid is a good acid to use for that buffer solution to keep that pH of 5 or near 5. So here's our mechanism to add an amine to an aldehyde or ketone, and then a little bit of an explanation of why we use a buffer solution here.